Okay, everybody. So this is a look at section 4.5 and 4.6. This one's going to be a little bit tougher because it's about the graphs. I don't know that there's specific processes other than we're just going to talk about a bunch of things. So let's talk first about this. So we're going to look at graphs of secant, cosecant, and cotangent. I'll get those for you here. This is not one of them. This is something we're going to deal with later in the class. But let's go ahead and clear out this one. And we want to look at secant. So secant is 1 over cosine. So I'm going to go ahead and graph 1 divided by cosine of x. And I'm going to put it in just like that. And I'm not really sure what my window's at, so let's give this a little check. So my x-min goes from negative 10 to 10, and my y-min goes from negative 10 to 10. Sure, let's go ahead and look at what that looks like. So you can see that a cosecant is going to be related this way. And it's really hard to tell. You're like, why are these loops in here? But what I'm going to do is I'm going to put in sine, and you're going to go, oh, this is going to make so much more sense. Okay, so here's sine x, and I graph that, and that's going to be red. Hold up, sorry. I said I was going to do secant. I want to do cosine. So again, the top one, 1 over cosine, is secant. So I want to do cosine x. I'm like, looked at the graph and like, that is so not what I want. So we'll look at these one more time and we'll kind of have an understanding of why they look the way they look. So you can see that every place that the red function, in this case, one more time, cosine, and let me do this a little faster, speed this res up here. Okay, so evidently I can't do it faster. So again, it's really nice, but then you know that sometimes it jumps. So if you are a person who already had your calculator on fast, then know that jumping up our x-res right now and having it plot every 4 points really got us a yucky looking graph. So one more time here. So we know the red function is cosine, and if you think about it, we're going to take cosine and we're just going to flip it upside down right at each one of those points. And you'll see that as the red line gets closer and closer to the x-axis, you'll see that there becomes a almost a vertical asymptote right there. Well, that makes sense because if we have on our graph 1 over cosine x and cosine equals 0, 1 divided by 0 is undefined, and that's why we get vertical asymptotes for secant. The same reason why if we do this, and this will look, actually let me do them right here. So let's do 1 divided by sine x, and we'll do sine x. You're going to see that these are going to look really close to being the same, except that it's shifted just a little bit. Okay, so these are what these graphs look like, and you can see the same way that on these ones, the purple one flipped upside down gives you the black. Okay, so let's get rid of those. Clear, 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 and clear. We'll talk later about domain and range and stuff like that, but that's kind of what those graphs look like. So how are tangent and cotangent different? So let's go ahead and do y equals tan x, and give a graph of that. And you can see that tan x kind of goes like that, and instead of repeating every 360 degrees, it repeats every 180 degrees. And like, well, how can I tell that? So let's do it this way. Go to our window, and so x-min, we're going to make it be 0, and x-max, we're going to make it be 2 pi, and then graph. So you can see it starts right here and it goes up starts again from down there because it's got an asymptote because it's undefined when we have tangent of 0, which would be impossible. And then right here, it looks like it starts all over again. So if this is 2 pi, then it repeats every pi. So how does this look in comparison to the other ones? So let's do cotangent, and cotangent x is the same thing as 1 divided by tan x. And hopefully this will process well for you. And you'll see that these are basically almost reciprocal functions from each other. If a tangent function has a vertical asymptote here, the cotangent function has a vertical asymptote right there, and but it's still same repetition, 180 degrees. It still has rotational symmetry in one of those spots right there. So that's what those functions look like in general, and that's what I wanted you to get out of that. So you can put down any of that stuff in your notes in that area, but know that secants and cosecants look like that, and cotangents, where a tangent goes up like this, and from left to right it increases over that span. Cotangent, again this is the tangent, cotangent does the exact opposite. Okay, so hopefully that's good for you. So down here we're going to say, let's try a problem like this. It says find x, and it gives you y here, 400 feet here, and then it's a right triangle, and they tell you that y is 0.23 radians. Well, we'll put 0.23 radians in there the same way, that is, if I would put it in degrees. What I just have to make sure of is that my calculator's mode is in radians. So let's check my mode, and you can see it is in radians right there. Pop that up there for you. Probably blurry, but it still works. So I'm going to go back ahead and quit out of that. So I know that I've got an adjacent of 400 feet, hypotenuse of x, adjacent hypotenuse is cosine, so I'm going to do cosine of 0.23 equals 400 over x. You know that whenever you have the variable downstairs, you simply take it with these two and you flip-flop them. So you'll end up with 400 divided by the cosine of 0.23. So on the calculator, I'm going to do 400 divided by cosine 0.23, and I get 410.81 feet. And I'm going to dims that. I go, does that make any sense? And yeah, if this is 400 feet, that shouldn't be too much longer if I kind of rotated that down. The other thing is, I just drew a random triangle in here. 0.23 radians. If I wanted to check that, I could just convert it into degrees so that I would know exactly how much it is. So I simply multiply that by 180 and divide by pi. So 0.23 times 180, enter, and divided by pi, enter. And you can see that my actual angle is only 13.17 degrees, and this picture shows it a little bit bigger than that. Okay, if you wanted to check it with degrees, you could do the same thing, just so that it works out for you. So here we go, 13.717. I'm going to go ahead and store that in x. So we're good there. I'm going to go to my mode. I'm going to change my mode, change it to degrees, enter. And now I can do 400 divided by cosine of that angle, which I just put in as x, at 13.17. And you see I get this exact same answer, 410.818 degrees. Cool. Okay, so what happens when we look at some other graphs? What happens when we're not just doing sine, cosine, or tangent, or we're not doing the reciprocal functions? So what we're going to look at right now is one of these things right here. We're going to look at sine squared x. And I know in trig you did a lot of stuff with sine squared x. However, I'm not so sure that you did a lot of graphing with it. So when we input it into our calculator, we have to put it in like this, and put it in as sine x and have the square on the outside of it, not the sine of x squared. Okay? So again, sine squared x, like we've talked about in other things, goes in just like this. So I'll give you the first little feel for this thing, and we'll go here. Let's go back to radians, because I was in the regular mode for the graph for that. And I'll go back to my y equals, and then I would do, so sine squared x again looks like this. Sine x parentheses squared plus cosine x parentheses squared, and you guys might be having a little recall right now. Sine squared x plus cosine squared x. I think you guys remember this. It equals 1, right? So if you watch and I hit graph, you can see that it is a horizontal line at 1. Okay. So if we were to put them in like that, let's go ahead and delete all this stuff. And I said that I would do this sometime. So here's a shout out to all the moms out there who I talk to during parent-teacher conferences that say that they hear my voice off in the dining room table or off in the kids' rooms. So I hope you guys are doing okay too, and keep supporting your kid and their learning. Okay, so here we go. So let's do sine squared x just like this, and I go ahead and my window. Let's make the y min -2 and the y max 2, and we'll go ahead and graph there. So you can see that when I've squared it, and I hope this makes sense, that all the things that were positive are positive, and all the things that were negative are now positive. So when I do a sine squared x, that entire function is directly above. So watch, when I do this one on the next line, so I do cosine of x close parentheses squared, and you can see that they almost make like a DNA strand right there. Isn't that kind of nice? And that if you add those together, when the first one's 0, the other one's 1, and that adds to 1. When they're both a half and a half, that adds to 1. And that's why these two functions, pretty cool looking graph right there, do that. And if I was to spread it out a little further, I get that going all the way across my screen. Okay? So then one of the things in my notes, it says to discuss what a period is. So a period simply means that that graph at some point in time starts to, wherever it is, starts to repeat itself. So if it can go from one spot to another spot and it repeats itself, then that's considered it being a period, which means that it's considered a sinusoidal graph. So something that repeats itself over and over again. And we're going to start looking at different graphs of different stuff. Okay, so before we do that, let's discuss domain and range of sine squared x. So let's get rid of this sucker here and here. So what does domain and range mean? So domain and range simply are what can we put in for x. That's domain. What's legal to put in for x. And I believe it's everything, right? I don't know that there's anything that we can't put in there. And you saw when we just graphed it, it went like this, right? That every x, that every x is available for that. So on that domain, that would be all real numbers, or everything from negative infinity. You'd think the text asks you to put in some of this stuff like that, negative infinity to positive infinity. Whereas the range is what values can you get out of y. So these ones go from 0 to 1. So the range on this one is 0 to 1. And then you guys know that we talked about some other stuff with this. So what happens if I come up here and I insert a 5, for instance? So then I go to my window and I go to my y min and make that -6, and y max and make it 6. And then now I go like this, and you can see that now my domain doesn't change at all. Everything's still available as I go from left to right. But the range goes from 0 up to 5. And the reason is that there's a constant multiplier of 5 up here. Or in other words, it affects its, what was the word we used? Its amplitude. Whereas, if I was to do this here, 5, and just do sine x, I would also see it go all the way up to the same high point, but all the way down below 2. It just so happens to be when we square it that all these negative ones become positive. You can also see that the curve going up is a little steeper when we're doing the squaring compared to that. Okay, so now what's next? What's going on with these graphs that we've been looking at? So we're going to discuss something called oscillation. And we're going to look at this function first, y equals x minus sine x. So go ahead and type that into your calculator right now. Clear that out, and we'll clear that out. And we'll get y equals x minus sine x. And graph. And you're looking at that and you're like, what the heck's going on with that? So I'm going to check a couple things here. One, I'm going to go to my mode, and I'm in radians. I'm going to go to my window, and I'm going to see if I can bump that out a little bit here. Zoom 6. And if you look, like, what the heck's going on with that thing? And I just got a sine wave that keeps on going up. Well, the reason it keeps on going up is because I'm subtracting sine x, which is the same amount each time, right? That just is a repeating function or a period function sinusoidal model. But I'm taking it away from x. So as x gets bigger, say it's 5, it'll be 5 minus something, and then 6 minus something, and 7 minus something. So it's going to keep getting higher and higher and higher. And you can see with this, if I go ahead and graph this, I can graph x plus 1. And I can graph x minus 1. This is kind of cool. You'll see that this function basically is just a wave that goes up and down in between these two parallel lines, which means that it's oscillating. It's going back and forth between two different things. Okay? And if I wanted to make that, of course, bigger, I could do that. Say that it was 3x, second function insert a 3, and then graph like this. You would see that that line does the same sort of thing. I didn't change the other ones, just notice that it doesn't go there. So it's going to oscillate, except it's going to oscillate between ones that are steeper, like that. And last time on the graph, and if I blew up my window and zoomed out quite a bit, you'd still be able to see that. Okay? In fact, I'm going to go ahead and do that. I'm going to make the x's -5 to 5, but make the y's -30 to 30. And then graph, so you can still see there is, it almost looks straight because it's zoomed out so much, but you can still see that it goes back and forth between these same parallel lines now. Okay, so that's what oscillation means. So then the next topic that we're going to get to is something a sinusoid? Well, 4 cosine x plus 2 sine x, that looks pretty weird, but it's just a really steepish, I don't know, cosine function, so amplitude of 4, plus a sine function, amplitude of 2. If it's a sinusoid, both parts of the period, whether through sum or differences, do that, if both parts have a period. So I ask you, does 4 cosine x have a period? Does it repeat itself? And you're like, yes. And they say, well, about 2 sine x, does that have a period? Yeah, so that means if we add these two things together, or if we subtract these two things together, then it also should have a period. So let's go ahead and try that right now. So we're going to go here, and clear, and clear, and clear. So 4 cosine x parentheses plus 2 sine x and close parentheses and zoom 6. So you're like, ooh, that's funky looking. But I guess my question is, does it repeat itself? And you're like, yeah, it does repeat itself. So it does have a period, which means it's a sinusoidal model. Okay. Well, what if I had this? What if I had this, and then I put here plus x? Well, does x have a period? Well, no, x is a straight line. So if I was to graph this, you would see that I would have something that looks like this. And every time as we did this, it would keep growing and growing and growing, which means that from left to right, it will never be identical to what's going on. Okay? So in other words, this hump right here is not going to be the same place above the x-axis someplace to the left. It's going to keep growing and growing and growing and growing. Okay, so that's the difference between being a sinusoidal model or not being a sinusoidal model. Okay, so what happens on these last things? So we're going to talk about something called damping factors. So if a function f of x equals x cosine 4x, we're going to look at the graph first before I talk about that. So let's go ahead and look at the graph. So we've got x cosine 4x, x cosine 4x. So x cosine 4x. And this is going to look weird, but let's go ahead and hit the graph. You're like, what the heck? And now you'll notice that this is the exact same graph that we started off with when I was first pulling up this stuff. So a damping factor means that the waves are going to get really, really small in one direction or really, really large in one direction. So this one definitely does have a damping factor on it, and that's how we know it. Again, it's going to approach, going to get smaller and smaller waves or larger and larger waves. And we're just wondering where the damping occurs at. So the dampening means where it gets smaller and smaller. So this one's damping as x approaches 0. So it does exhibit damped oscillation. So oscillation means going back and forth. Damping factor is x. This is the thing that's doing it right here of cosine 4x. And it dampens as it approaches 0. So there's going to be different ones that you can do, and go ahead and put those in different graphs from the assignment and stuff. And, honestly, go around and just play with some of these different graphs. Play with secant or cosecant or cotangent, just to see what they do. As we've gone through this today, we've had, again, sine waves that repeat, and then cosecants that go opposite of what they are. Like if I was to do this one, I could even do this. This would be pretty messy, right? I'm going to go ahead and insert 1 divided by all of this stuff. Still got to keep that inserted. I'm going to put parentheses. I might do that whole thing. So 1 divided by that whole thing. So when I do graph, you're like, what the heck? Got some weird looking stuff right there. But you can see that these little humps are closer and closer to the x-axis way out here, and they're further and further away from it right here. And also, if I wanted to put this in here, second function, insert maybe a 5 in front of that, and look at that same graph. And you can see now that even my calculator, I can't imagine what it's like on an 83, is starting to have issues with these things. It can't plot all of those different points. So if I wanted it to go here, I might go ahead and insert a decimal place. but instead of my window of going negative 10 to 10, I might just go 0 to, say, 3. And now you can see it a little bit better. We're just going to highlight some of them. So you can see each one of these little humps is getting closer and closer to the x-axis. So again, play around with it, see what it's like on the homework questions, and have yourself a great day. Thanks a lot for watching. This is Mr. Bells.